So in this problem we're given this matrix, which I've given a name, I'll call it capital A, and it's a very specially shaped matrix. It's got lots of ones above and below. On the main diagonal it's got the real number A. Of course the first thing about it to note is that it is a symmetric matrix, and so that means the eigenvalues are all going to be real, and the eigenvectors from distinct, the word distinct is important, from distinct eigenvalues, those eigenvectors are guaranteed to be orthogonal. So the first job when it says orthogonally diagonalise A, we have to find an orthogonal matrix P such that P transpose AP gives me a diagonal matrix. So to do that we have to find firstly the eigenvalues. So I'm going to do that. I'm certainly not going to work out determinants. I'm going to do that by inspection. And I can see that I've got to think, what can I subtract off the main diagonal? What can I subtract off the main diagonal that will make the determinant 0? Well, it's pretty obvious. I need to get rid of this A. And so I'm going to subtract A minus A. That would give me zeros down there. That won't quite make the determinant 0, but if I put A minus 1, then when I subtract A minus 1, that'll give me 1s along the main diagonal, and the determinant's definitely 0. So that's going to be the it's going to be at least one of the eigenvalues. So once you've got an eigenvalue, you then look at the corresponding eigenspace. So the eigenspace for this eigenvalue is going to be the kernel of this matrix. So to look at the kernel of this, I notice that the rank of this matrix is 1, because if I were to row reduce it, I'd get one row and all zeros below. So it's got rank 1, and that means nullity is going to be 3. So this is rank 1, and the nullity is going to be 3. And that means that the eigenvalue, lambda equals A minus 1, has algebraic multiplicity at least 3. Might be exactly 3, but at the moment at least 3. So I can actually write down 3 of the eigenvalues. They're repeated, and so I get those 3. Now, so having got that, I need to get 3 eigenvectors out of this kernel. Well, I could do something like this. I could write down the eigenvectors as 1 minus 1, 0, 0, 1, 0, minus 1, 0, and so on. I could write those down, but then because it's a repeated eigenvalue, there's no guarantee that those eigenvectors are going to be orthogonal, and I want them to be orthogonal. So I'm going to do what I call creative cookery. I'm going to cook up the eigenvectors from this matrix, but I'm going to cook them up in such a way that they are orthogonal. The theory will not guarantee that. It will when I get the fourth eigenvalue, fine, but not for these because they're repeated. So I'm going to cook up 3 vectors in the kernel, and I want to try and make sure they're in the kernel of this matrix, and I'm going to make them orthogonal. So start off with something simple. So I'm going to start off with 1 minus 1, 0, 0. It's obviously going to be in the kernel, and so that's an eigenvector. Now when I come to the second one, I want the vector here to be orthogonal to that one. So forgetting about what goes here for the minute, I'll really need something like 1, 1. Don't care what goes there at the minute, because orthogonally if I take a dot product, I'm multiplying by 0, so that's going to be orthogonal to this one. And then what I'm going to do is I need to cook up to make sure it's an eigenvector. So at the moment I have 1 plus 1 is 2, so I need minus 2 there to make sure it's an eigenvector, and then I'll just kill the last entry. So just note that, creative cookery. You cook it up very carefully. Well, finally, I want another vector orthogonal to both of those and in the kernel. So same idea. You'd better start out as 1, 1 to be orthogonal to the first one. If you look at this one, I get 1 plus 1 is 2. I'm going to need a 1 there to make sure it's orthogonal with this one, so that I get 1 plus 1 is 2 minus 2 gives me 0. And finally, I need it to be in the kernel of this, so when I dot product with each row, I've got to get 0. So at the moment I get 1 plus 1 plus 1 is 3, and I'll need a minus 3. Okay, so I've cooked up my 3 eigenvectors, and they're all mutually orthogonal. Well, there's 3 of the eigen values. I need to get the 4th one. So from the trace, the 4th eigenvalue, well, what's it got to be? I add up the sum of these 3 plus the next one has to add up to that. And so I'm going to need an A, so when I add these, A plus 3. So that when I add this one plus each of those, I get 4A, and that's the trace. Now I need to get the eigenvector from here, so I need to look at the kernel. I'm going to subtract A minus 3 off, so I'll get minus 3, 1, 1, 1, 1 minus 3, 1, 1, 1, 1 minus 3, 1, 1, 1, 1 minus 3. So I need to get the kernel of that matrix. Well, you can do row reductions on it and fiddle around, but if you just stare at it for a moment, a little bit of thought, you'd probably be able to guess what the vector is. I want a vector that when I multiply by the matrix gives me 0. Well, notice that in every row, if I just add those numbers, it cancels with that. If I add those, it cancels with that, and so on. So if I just take 1, 1, 1, 1, that will do the trick. Now, by the way, remember that the theory guarantees that the eigenvectors from distinct eigenvalues guaranteed orthogonal. So I didn't have to do anything fancy here. This must be orthogonal to these ones, and if you quickly check it, you'll see they are orthogonal. If you dot product, you get 0, 0, 0. That's guaranteed by the theory of symmetric matrices. So finally, I would put P then. I can put P. I now have to orthonormalise these, so be careful of that. So I orthonormalise these. I'll get 1 on root 2 minus 1 on root 2, 0, 0. This one's got length 4, 5, 6, so that's 1 on root 6, 1 on root 6 minus 2 on root 6, 0. This one's got 9, 10, 11, 12, so this is 1 on root 12, 1 on root 12, 1 on root 12 and minus 3 on root 12. And finally this has got length 2, so that's just a half, a half, a half, a half. So put P equal to that. Then if I work out P transpose AP, I will get a diagonal matrix, and on the diagonal will be the eigenvalues. So I'll get A minus 1, A minus 1, A minus 1, A plus 3, and then zeros everywhere else there. And so I've orthogonally diagonalised the matrix.